based on my bio, I'm not actually, I'm sort of a phony computer scientist. I came from the world of chemistry, so this talk will have some chemistry just for background and for your all identification. So I'm required, you can still see this, right?
Yeah.
Okay. So, save that just for record. So you guys are probably familiar with this. It's a whole lot of fun. I'm not going to read it. It's not really pertinent to this talk, but it has to be there. I will say this one. I work for Intel Labs, so if I say stuff about products, which I probably won't be, I'm not any more credible than the next guy. And these are all my own opinions. In fact, a lot of this talk is based off the stuff I did in Argonne. So it's not any sort of Intel official thing. And, you know, especially in this talk, I'll say that individual performance numbers may be difficult to reproduce. But the good news is all the code is open source. And actually, the fourth bullet isn't true in this case, but it is old stuff. Anyways, so I have two collaborators on this project for a very long time, since the beginning. Dinan is my good friend, who is actually an alumni of Ohio State from today's group. Wrote the original version of ARMCI-MPI while he was in Argonne. He proceeded being leading for Intel. And then Balaji, who is, of course, an alumni from DK's group, has been working on this project as well. So Jim wrote the first version, and then I wrote the second version. So that's the difference here. So, real quick, to talk about sort of motivate the work we're doing from the science perspective, there's three buckets of chemistry that one wants to solve. Classical MD, which some of you might be familiar with, maybe mini apps, then density functional theory, and then quantum chemistry. And they have different algorithmic and software properties, and we'll see that in a second. So if we look at classical MD, the sort of challenge here is it's small data, so not big data. The opposite end of the spectrum, it usually fits in cache and strong scaling. But the calculations are latency sensitive and they're load balanced. And so what you'll see in sort of the advanced codes like the MD is they use R++ to deal with load balancing, to hide some of the latency and overlap communication computation. And then two of the other big codes are sort of traditional MPI plus X codes. And they can suffer in the limit of loading balance. Density functional theory, Car-Parrinello molecular dynamics, is much more bulk synchronous in nature. So essentially all the codes in that space are written in MPI-1 traditionally, maybe threading in the math libraries. But there's a decent amount of data, but these algorithms are relatively straightforward to do distributed computation, scale back, and then with this one. Now, when we move into quantum chemistry, we have a bunch of different methods that fall under this umbrella, but we see that despite sort of different physics and different mathematics, they're all either somewhat large data or are irregular. So if we look at a Hartrich-Bach method, there's an IPDPS paper, 2013 by Edwin Shaw and Jordan Check that has a very, very nice work. It's actually a very new algorithm based on global arrays. So some of that has informed what we're doing with ARMCI-MPI, and we scale that way out. That tends to be small messages, not 8 bytes, but definitely less than a megabyte, probably in maybe 1 kilobyte range at most. But they're highly irregular and they're dynamic. If you look at Copper Cluster, which is my particular preference, these are not dynamic computations in the sense that they don't evolve their load balance with time, but they're incredibly irregular from a block sparse standpoint, and they have extremely large data requirements, often distributed arrays into the terabytes, and they lead to bandwidth limited computation. And then quantum Monte Carlo, which I won't really talk about at all, is quite regular, but still has a data footprint that in some cases motivates the use of gas and has had a global arrays component in the past. So the motivation for using a global arrays programming model in these simulations is that these are dynamic, irregular computations, or in and/or they have data in excess of a process or what a process or a node can handle. Obviously, you're limited by the memory per process if you don't have threading, which a lot of legacy codes lack thread. So that's the motivation. I'll come back to global arrays in a little bit. So just NWChem, for those of you who are not familiar, is a widely used open source package. It's been around for 20 plus years. You can find most of this stuff out online. It's got an extremely diverse collection of functionality, so it's not just a code that does one thing. It's used by a bunch of, huge range of applications: catalysis, biology, material science, geochemistry, you name it. The chemists are using it for something. We even actually use it internally at Intel, although I probably can't describe the chemistry that they do with it. And it's extremely affordable. So it runs on everything from my Mac laptop to InfiniBand clusters, of course, which are of most importance to this crew, and on custom supercomputers, which of course nowadays aren't as exotic as they used to be. They tend to be, like big supercharged clusters, creating blue gene among them. That's NWChem. It's very important community code, and it's one of the codes that scales to large machines, and that's so a lot of people use it because it's the only code that will scale to a large machine, even if they don't necessarily like it on their laptop. It's an older code, so it began actually before MPI, which is has had a pretty substantial impact on its design. It also existed before C++ was remotely common, except it's trying to be C++, so it's object-oriented Fortran 77, which, a little bit of a crazy concept, but they do their best. And they actually NWChem was co-designed with the global arrays programming model because there was a desire to abstract away the sort of process-centric, CSP style programming in favor of something that was data-centric. So global arrays focuses on distributed arrays and what you do with them. So if you have a distributed array, you want to diagonalize it or you want to set it to 0, there's just a single function call for that. You don't have to program up the data parallelism for it. And then, of course, there's fundamental one-sided primitives, but they act on the sort of the global data and the global indices, so the programmer doesn't have to think about where data is. Global arrays manages that for them because it's one-sided. You don't have to satisfy the sort of matching criteria of Sanderson. And it has a whole bunch of custom runtime layers because of its history and needing to be extremely portable, running on crazy machines that nowadays are only in museums. So it has its own memory allocator, an IO layer, and of course, this talk has its own communication runtime known as ARMCI. So, one of the things one could say at this point is, well, NWChem sounds like it's got some weird words. Why don't we get rid of it, try to start over so we don't have to deal with ARMCI if ARMCI is a problem, which I'll talk about in a second. It's actually harder than it seems. And the fact is, it doesn't matter because if we wrote NWChem from scratch in C++, you still want to extract away communication in a global arrays model. You wouldn't see the MPI. And the fact is, what we're going to show here, we're going to be able to drop MPI in behind the scenes, change the fundamental portability in the communication software, and NWChem doesn't actually change a single bit. So, some science highlights. This is just to say this is what people like to do with it and why NWChem continues to stick around and why it's important to get portable to the new machines. These are all things that I did, so they're obviously highly parochial for me. But they're important simulations, not just benchmarks, mood board, and belt prizes here. These simulations, of course, are only running on hundreds or thousands of cores, but they need to run for a long time, and they need to run very stably, at the memory limit because of the large data. I've actually run simulations for 6 days on an InfiniBand cluster because they didn't strongly scale. So, 6 days is a long time for the code to run without overwhelming the memory and cycle. So, anyways, so global arrays. This is the sort of higher level programming model. It's data centric, so you have the notion of a global address space or a global index space that's shared across all processes, and then you fetch data to your local process, you compute on it, and then you send it back, you update, whether it's a put or an accumulate. You're basically doing check-in, check-out, or check-out, check-in, and it supports distributed arrays with regular and irregular distributions all seamlessly, so you don't have to manage that explicitly when you're in the communication part of the code. You only manage that once during the creation of the array. So the style of programming that this leads to, this is, of course, a trivial example of matrix multiplication that doesn't require one-sided. Of course, people know that you can write summa or canon with simple MPI, but this is a template that can be adapted into much more complex algorithms, and especially ones that are irregular. So if you imagine adding a block sparse criteria to this kernel, you don't actually change the template very much. You just put in an if statement, and that next val call is a centralized dynamic load balancer. It will just basically, up until the limit of overhead, will balance the computation. So the good news is you get dynamically load balance computation effectively, and you get good weak scaling. Bad news is this template is a little bit, it ignores locality and topology. You can see that it communicates excessively in some cases. And in this case, it's ignoring a higher level structure of what matrix multiplication is and how it can be done, optimized using MPI collectives. But MPI collectives require a level of bulk synchrony that isn't often present in the real chemistry codes. And that's why this template is quite common in NWChem. And this is essentially the core of the way the routines in NWChem are written when they're not making math library calls or doing other sort of trivially bulk synchronous data parallel style computation. So going from global arrays to ARMCI, global arrays, like I said before, takes a matrix object and global indices. So if you have a million by million matrix or something, you can look for any of those elements, and you don't have to specify a process ID. Global arrays internally will translate that information to the remote rank or the local rank, or the holds the data and the virtual addresses and the size or the striding pattern because it's always arrays. If we contrast that to what MPI does, MPI sends feedback from ranks, virtual addresses, and sizes, much like ARMCI. One of the challenges for ARMCI-MPI is that MPI RMA acts on handles and offsets, but that was a problem that Jim solved. It was non-trivial, but fortunately it didn't change from MPI-2 to MPI-3. You still have to be able to translate from virtual addresses to a window object. So that's that build. So not all global arrays calls go to ARMCI, and if you have a global arrays call that is collected, it will drop into MPI. Obviously, scale-back uses MPI. So MPI has to be completely interoperable. MPI and ARMCI have to be interoperable. And that's something, of course, the MVAPICH group knows all too well. The challenges of interoperating MPI with PDAS runtimes like NWChem, GasNet. There's some serious runtime challenges. So one of the things that ARMCI-MPI does is it makes that runtime interoperability trivial because everybody's using MPI. So the ARMCI problem, which is the core motivation for this talk, ARMCI is unlike MPI, is not automatically portable. It's not a community standard that all the vendors implement. And it is the bottleneck at this point of porting NWChem to new platforms. There used to be some challenges if we had funky OSs or compilers, those are pretty much gone. So how does one achieve portable communication? Well, there's, of course, the other portability layer that people know about, TCP/IP. It's not a very good performing model, and it isn't available on machines like BlueGene or the supercomputer, so it's not portable in HPC. Of course, there's the model that has been pursued in the past, which is to write a new native port for every network. And if you can sustain a large enough team over an indefinite period of time to do that, it's feasible. but it is expensive to do those ports, especially in research group. There's two different MPI-1 based portability layers. One of them uses COMS1 and the other uses MPI-3 multiple. I'm sure the MPI implementers in the room know that neither of those functions are already at a good time and supporting thread multiple. Of course, they put a lot of overhead for mutual exclusion. So the last one, of course, is ARMCI-MPI, which is a new implementation of ARMC that uses MPI RMA. So it's the only one that uses MPI RMA. But of course, historically, MPI RMA has been a challenge for correctness, functionality, and performance. Fortunately, the situation has gotten much better in the last few years, and I think MVAPICH is one of the implementations that's had very good one-sided support and made this sort of stuff possible on interesting systems. So I'm going to talk a little bit about the MPI-2 port because we have a lot of comparative data with the original implementation. This is InfiniBand. So what you see here is the name is the dash. Okay. Well, you can see the figure. I wish we would have called the maps a little better. Anyways, there's two different components of NWChem noted here. The blue is the iterative part, and the red is the non-iterative. And what you see here is the native port is faster. In fact, it can be faster by quite a bit. And that's because in this case, the ARMCI-MPI port is really optimized. The problem is, in this case, sometimes the ARMCI native port is a little bit unstable because it registers pages so aggressively that it runs out of them in some cases. So in that case, having MPI run up slowly is better than nothing. This is CRAHT5. This is extremely strong scale. What you see is the scaling curve is about the same, which is a good thing, but again, the native port wins. This is bridging. The gap here is a lot smaller because the native port and MPI were using the same low-level primitives. We were really observing there is some semantic overhead with MPI. And then lastly, this is actually the case where we first won. This is a CRAHT6 where the native port had some serious issues, and MPI RMA isn't necessarily the best one on the planet. They do a very good job with the PGAS model, but MPI-3 has not been one of them historically. And so we get a performance win in some cases. So this was very encouraging. So you guys probably all know quite a bit about MPI standards, so I won't go into a great deal of detail about the mapping here. But one of the big issues for MPI ARMCI-MPI with MPI-2 is that there was no atomics, no line blocking, local and remote completion were fused, couldn't exploit symmetric memory. The memory model itself was constraining, and there's no way to aggregate synchronization. So what we see in the MPI-3 standard, which Tom and Jim and I were helped to define MPI-3 RMA because of what we learned from RMC. There's atomics. We now have blocking. The flush allows you to separate local and remote completion. Plurality allows you to use shared or symmetric memory. Memory model allows you to split cache coherent systems effectively. And then there's Winlock all shared, which is the one we're using all the time in global. So now we have, I apologize, the results are a little sparse just because in some cases, basically, I couldn't do a direct comparison. And in fact, the MPI-2 and MPI-3 results are not always as different as one would imagine. So we would have expected next block performance, which is where the atomics are used, to change dramatically. However, one of the advantages of the old version, which was not atomic, it uses a mutex, was the mutex was fair. It's an MCS block-based approach, and because it's fair, it actually delivers very consistent performance, even if it's low. And that has some advantages at strong scale to not have sort of crashing on the locking systems. The separation completion doesn't really change things on end-to-end networks. The non-blocking support did make a big difference on channel pad 2, but otherwise doesn't show up a whole lot. And the window memory is sort of a mixed bag. So what we've observed, and I'm getting close to the end, hopefully I still have about 5 minutes, is some of the things that we did didn't change so much. In the case of the shared memory Windows or the shared memory packing for Windows, I actually managed to hit essentially every bug in MVAPICH along the way, which of course went downstream into Cray and MVAPICH. So I've had to disable. So this is ARMCI over MPI-2. I'll show MPI-3 in just a second, and then I'll put them on the same deck where it matters. So the performance here, if you look at the raw data, it's pretty good. It's comparable to the native port. This QBR InfiniBand, we're getting 2 gigabits a second bandwidth at the high end or close to it. The latency is on the order of a microsecond or 2. It's exactly where we'd like it to be. MPI-3, you see the curve changing, and then we'll zoom in on that in a second. It's basically the same story. These are contiguous benchmarks. There's nothing special, and MVAPICH doesn't go with RMA. No surprises. So what's it to me, and this is sort of my question for the audience for offline is, it turns out that the performance of accumulate goes down when we turn on MPI-3. So in MPI-2, we use MPI win lock, win unlock, with lock exclusive. But when we go to MPI-3, we don't have an exclusive lock, we have a shared lock, and we use flush. And we see that this causes, in the case of MPI-3, I guess using the shared lock, presumably and not flush, but I don't know for sure, causes a bandwidth hit for larger messages. And then of course at the 2K or 2 megabyte boundary, I think we get a cache effect. So one possible optimization there, I guess, is pipelining, and we could do it in ARMCI-MPI or MVAPICH could do it. But this is the sort of biggest performance artifact that I have to present. Everything else is pretty much boring and not worth wasting slides. So the other part of it is ARMCI-MPI performance. This is my favorite all-time quote in all of computer science. Hopefully people can read it. It's having code that works is more important than anything else in the world. You can have fast code that crashes. It's not very helpful. This is the big benefit of ARMCI-MPI. So here's the route performance that we've observed. So there's no native port on Chapter 2, which of course is the best machine in the world. They have an MPI-3 implementation, however, it's based off of MVAPICH. We've scaled global arrays code to 8,000 nodes, which is a third of that machine. There's no native port on Notion Q. There's also no MPI-3 support until very recently since I left Argonne. But ARMCI-MPI worked just fine for what we needed to do with NWChem. The native port on InfiniBand for me has been extremely unstable. On the other hand, on Mellanox systems, MVAPICH I've literally never seen a crash due to the communication conduit, except when I needed to tune some environment variables. And I'm running out to the full memory limit without having any instability to people. And then the same story is true on Cray. The native port is quite fast, but it crashes for me about half the time, including all of the time in the part of the code that I want to run. And ARMCI-MPI is going out to 80,000 cores without a single crash. So there we've got 2 examples of there isn't any native port to compare to, and in the other 2, it's native port does port all the time, and thus we sort of have performance motivates using ARMCI-MPI. So the last, so in conclusion, so MVAPICH 2 is one of the first implementations for HPC networks. It's supported MPI-3. I've been using it for so long I can't remember, and there's a number of science papers that have already been published that made use of MVAPICH for the Cray version with ARMCI-MPI running NWChem. ARMCI-MPI has enabled us to run NWChem on platforms that we couldn't run on otherwise. There was no native port, and in the case of John Hay, there isn't like a V1. MPI-3 has been somewhat of a, not disappointment, but sort of frustration for me because of all the implementation bugs I did. Of course, that's how life works. MPI-3 is a new standard, and all the implementers are, of course, learning how to balance optimization and sort of correctness and functionality. if someone writes a good data report, it will be faster. It's, of course, questionability and the existence and improvement. So I still maintain the wiki on the MPICH website for ARMCI-MPI. ARMCI-MPI is now a separate repository, but is still part of the MPICH family of nodes. And the website has lots of documentation on how to use it within NWChem and some of the reports that are required to get it running on various platforms. That's it.